Hello everyone, thank you very much for attending this presentation. I'm Andreu Cecilia, PhD student from Institut de Robòtica and Informàtica Industrial, Barcelona, Spain, and today I will be briefly presenting our work entitled On State Estimation in Weakly Observable Scenarios and Implicitly Regularized Observers. So this work evolves in the context of designing an observer for linear systems with possible time-varying matrices and possible some sensor noise. In order to simplify the notation of this presentation, we will assume that the system is autonomous. However, it should be relatively easy to extend these results to the case that there are some measured exogenous inputs. So the main difference between what is considered here and the vast literature on observer design is that here we consider that the system is weakly observable. What does this mean? So let's consider the observability gramming of the system. It is well known the concept of complete observability. That means that the observability gramming is upper and lower bounded. With this condition, it is known that if you, for example, design a Kalman filter, you can prove analytically that the estimation of the Kalman filter converges to the true value. However, this work considers systems that are completely observable, so the observability gramming is upper and lower bounded, but are weakly observable. That means that the observability gramming is illposed, which means that the minimum singular value is close to 0 or the condition number is far from 1. In order to understand the consequences of this weakly observability, let's transform the state estimation problem into an optimization problem. So we can relate the current value of the state with the past values of the output through the fundamental matrix of the system using the first equation in this slide. If we pre-multiply this equation and integrate through in some time range, we get the second equation of this slide. Then we can see that the state estimation problem is just the problem of isolating the stage from this second equation. And we can present this an optimization problem. This is what we have in the last part of this slide. If the system is completely observable, then there is a unique solution to the state estimation problem. And this is the property that you want in observers. However, if the system is weakly observable, so the matrix is illposed, then this optimization is also an illposed problem. So you will have numerical issues trying to solve this. To exemplify this, let's consider a very simple second-order system depicted by these matrices A and C. By some computation, you can show that the eigenvalues of the observability gramming satisfy the following conditions. First, the minimum eigenvalue converges asymptotically to 0, and the maximum eigenvalue converges asymptotically to infinite. So if you consider any time range that does not include the infinity, you can show that the system is completely observable. However, it becomes weakly observable with time. So as the system is completely observable, let's try to design a Kalman filter. So let's try to solve the optimization problem of the last slide, and the iterative solution becomes the standard Kalman filter. However, here we consider a slight modification because in the P dot dynamics, we have included a minus mu multiplied by P factor to try to include some gain to tune in the observer. Why? Because maybe the system becomes weakly observable with time, but we can converge to the true value before the system loses the observability. However, as we can see in this slide, this approach is not adequate for this system. In this solution, in the blue line, it is depicted the evolution of the second state, which is constant, and then the estimation of different Kalman filters with different values of mu. We can see that when mu is 0, the estimation converges to a value that is different from the 2-1. And it is true that as you increase mu, you are reducing the error of the estimation. However, at some point, the estimation is practically useless. Why? Because you are combining two issues. First, by increasing mu, you're increasing the gain of the observer. And it is well known that increasing the gain increases the noise sensitivity of the algorithm. And second, the Kalman filter is implicitly solving an illposed inverse problem. So you will have numerical problems with that. By combining the two issues, you get that the state estimation is practically useless. So this work tries to propose an alternative route that can be implemented in these weakly observable scenarios. To understand what is being studied here and why it works in these cases, let's consider the idea of regularization. So it is well known that if you have an illposed inverse problem, that is what we are having here by having a weakly observable scenario. So in illposed inverse problem, you can significantly increase the conditioning of the optimization by adding a regularization factor. So assume that we have this optimization problem of the last slide, but we add a regularization factor there. Then you can show that the solution of the optimization takes the form of this second equation of this slide. You can see that even if the observability Gramian is illposed, so inverting M transposed M is difficult, by adding a small factor pi, you get a matrix that is much more simpler to invert. So with that, we have improved the conditioning of the estimation problem. The objective of this slide was to show why in weakly observable scenarios, regularization may be the key topic to study. However, this work will not pursue this idea exactly like this. It will propose an alternative route that is based on designing an observer that you can prove analytically that it converges, and you can prove that it solves implicitly an optimization problem of a function to be designed by the designer. With that, you're implicitly regularizing the estimation problem. So to achieve this design here, what we're going to do is combine two ideas. First, we are going to transform the state estimation problem into a parameter estimation problem following the ideas in this reference number 1. And second, we are going to estimate these resulting parameters through a natural gradient descent algorithm. That this will implicitly solve an optimization problem to be designed by the designer. This natural gradient descent-like algorithm will follow the result from this second reference here. So let's start with the first part, transforming the state estimation problem into a parameter estimation problem. So we will consider this chi.dynamics here. In general, you cannot initialize this chi value at the same value of the stage because you don't know its value. So you will have some error signal dynamics that you can compute through the fundamental matrix. So this is the second value here. We can see that through the fundamental matrix of the original system, we are relating the initial value of the error and the current value of the error. The idea is that if we take this initial value of the error, which is constant, as a constant parameter to be estimated, and you achieve an exact estimation of this constant parameter, then you can reconstruct the states through the last equation of this slide. So how can we transform this second equation into a parameter estimation problem? So we just define this y tilde value here, and then you can show that the equality in the second equation here is satisfied. It means that y tilde is equal to this factor c multiplied by the constant initial error. So we can see that this is just a linear regression, and you can design any parameter estimation algorithm for linear regression to estimate these parameters. Naturally, if you implement a least squares algorithm, you recover the Kalman filter. What we propose here is to use a natural gradient descent-like, which will implicitly optimize a function to be designed. So what does this mean? Let's define this set omega here, that is the set where the error between y tilde minus c and the estimated parameter is lower than some value that depends on the noise. Obviously, most parameter estimation algorithms that you can show that are stable will converge to a set of this form. What we do is design a strongly convex function phi, and then implement a natural gradient parameter estimation which takes the form of the second equation here. It can be shown that then the estimation not only converges to the set omega as most parameter estimation algorithms, but also minimizes this strictly convex function phi. What does this mean? That the estimation not only converges to the set omega, but converges to the subset of omega that minimizes the value phi. So this is exactly what we want. We are reducing, even if you have a nil-post inverse problem, so the set omega is large, you will converge to the subset omega phi. So you will implicitly regularize the state estimation problem. So to show, to see the advantages of this approach, let's recall the problem that I presented before. So we have this second order system, and we can see that if the estimation of the output is initialized at the exact value of the measured output, then some values of the initial condition of the error will be 0. So it is reasonable to assume that by designing a parameter estimation algorithm that will promote a sparse solution, a solution with 0 will converge to a subset that is lower than any other parameter estimation or a most parameter estimation. And how can you promote a sparse solution? In the optimization context, it's well known that you can promote zeros in the solution by including a regularization factor that is the norm 1 of the parameters. You cannot directly implement this here because the norm 1 is not implicitly convex. However, you can design a function phi that is the norm plus 1 plus epsilon, with epsilon is close to 0. With that, you get the norm closer to the norm 1 that is strictly convex. Indeed, if we design an observer that implicitly minimizes these functions through the approach that we have proposed, you can see here that you get an estimation that gets really close to the real value. Here in the orange line is depicted the estimation of the Kalman filter that I presented before, that there is some error, and in the other ones it's depicted the estimation of the implicitly regularized observer with this norm 1 minimization. And we can see that without that relying on increasing the gain of the observer, that we know that this does not work, we converge really close to the true value. There is two estimations because in the document I presented an observer with some tunable gain, but basically the idea is the same, so I just skip this part here. So as a conclusion, we have shown that in weakly observable scenarios, the state estimation problem becomes an ill-posed inverse problem. It is well known that by adding a regularization to the optimization problem, you can improve the conditioning of an ill-posed inverse problem. So what this work has proposed is first, transform the state estimation problem into a parameter estimation problem, and then instead of applying a least squares algorithm, implement a natural gradient descent parameter estimation, which is implicitly minimizing a function to be designed. With that, you're implicitly regularizing the state estimation problem, which we know that improves the conditioning of the problem. We have shown these benefits in a very simple example in which the standard Kalman filter does not work. So thank you very much for your attention. I would like to thank the Control System Society, which have granted me a grant that has allowed me to participate in this Congress.